Okay, thank you for the introduction again, Ben. So today we'll continue our discussion of categorification at prime roots of unity. So before we start, let's briefly review what we talked about over the last lecture. So we started with quantum group quantum SO2 as a diagrammatic one-dimensional algebra depicted on the one-dimensional x-axis, if you wish. This is a one-dimensional structure where the multiplication is essentially given by horizontal composition or juxtaposition of pictures. So whenever the weights match, so let me use highlight pen to indicate. So whenever these middle weights match, the resulting multiplication gives you a non-trivial element that corresponds to the juxtaposition of pictures. And of course, it's subject to certain relations defined by Serre. So whenever you commute E and F and E, you pick up some error terms depending on the weight lambda. So, and for the important thing for small quantum group SO2 is that there is this nilpotency relation that E to the pth power is 0 when p is an odd number. Here I wrote k. So and likewise for f. Okay, so in categorification, as we have said, fits into the framework of topological quantum field theory. So what we do is we introduce an extra dimension, the time dimension, to study the evolution of these one-dimensional pictures. So you naturally obtain two-dimensional pictures in this story. So you introduce, as Aaron Lauda did, generators, the evolution pictures of E's are two copies of E's and F's, and between E and F's, the so-called cups and caps, and subject to the relations like the Neal-Heck relations among generators of E, and this bijunction bubble relation, reduction to bubble, and identity decompositions. Using these relations, we have seen that in the abelian case, or in the generic Q case, this graphical calculus of Lauda, or more generally Kovalov-Lauda-Ruquier, gives you categorification of UQ-SO2, or more generally UQ of a Kac-Moody-Lie algebra at generic Q value. And the original abelian decomposition of the EF decomposition relation in the PDG world becomes a Posnikov tower, if you wish, or a filtration of the modules. So let me go back. So in this case, becomes a filtration of cofibrant or projective modules, in this case of the EF, into subquotients, which are the right-hand side of the small quantum group. So that's what we learned over the last time. But now today, we'll continue our discussion of the small quantum group, and now I'm going to explain the important nilpotency relation of E and F. So that's the characterization of a small quantum group in this context. So why is E nilpotent? Or E to the kth power, E to the pth power, and F to the pth power is 0. So to do this, we recall some knowledge of the diagrammatic calculus from Lauda, which I'm not going to show you the proof, but inside this diagrammatic calculus as a PDG algebra, actually there's a PDG isomorphism of endomorphism algebras. So if you draw all E's, so let me think about, so what the left-hand side means, if you consider E's, many copies of E's, so n copies, and likewise n copies of E's in the bottom, so that's the, you're considering how this E can be evolved into the E to the nth power on the bottom can evolve into the E to the nth power to the top. So these are all the pictures you can fit in with dots, etc. Like this. But in the diagrammatic calculus in U, there is a slightly more complication, but it's not too complicated. You can add bubbles to the region on the far right. Okay, so this is all you can do. So therefore, the endomorphism algebra of E to the nth power is isomorphic to the Neal-Heck algebra on n letters, together with the algebra generated by bubbles. And from the exercises last time, if you have done that, this lambda is actually isomorphic to the symmetric function in infinitely many variables. And this is actually an isomorphism of PDG algebras. So if you deduce that a derivation on symmetric functions, and the derivation on lambda is given by the derivation on symmetric functions, as you have seen. Okay, and now let's analyze this neo-Heck part more carefully, because the lambda part is relatively easier to understand. So the neo-Heck part has an alternative description. It occurs as the endomorphism algebra of the symmetric of the usual polynomial functions in n variables considered as the symmetric function module. So if you start with the n variable polynomials, it's naturally a module, left module over itself. But now you restrict the left multiplication to the symmetric functions, a subring of the natural polynomial ring. So therefore, the endomorphism ring is isomorphic to the neo-Heck algebra. So if you want a slightly more geometric description, so the polynomial ring is the GLN equivalent cohomology of the flag variety and n-step flag variety, and this is just the endomorphism ring of the of this module over the GLN equivalent cohomology of a single point. So that's the more geometric picture where this comes from. And because we're regarding it as a module, and last time in the exercises, you have seen that we have many freedoms of twisting the differential gradient module structure on the rank 1 polynomial module. So we can twist it by d to the z to the n, d of zn, the module generator, by, sorry, here I'm missing, this is xi times zn. Okay, all right, so this is the differential gradient module structure, and you can show relatively easily that this is a PDG algebra isomorphism, that the neo-Heck algebra with the given differential action of d of a dot is 2 dots, d of a crossing is, as we have given, occurs as the endomorphism PDG algebra of this polynomial differential gradient module over the PDG algebra of symmetric functions. Okay, so let's analyze this module structure. So as a left module over the symmetric functions, the fundamental theorem of symmetric functions tells you that this is essentially a free module. Okay, so this is a free module with of size n factorial, and a particular basis can be chosen to be compatible with the p differential action. So it can be chosen to be this monomial basis where I1 ik is less or equal to n minus k and greater or equal to 0. Okay, so this is monomial basis over of this polynomial ring over the symmetric functions. And if you analyze the PDG structure, so you have this tensor product decomposition. So this is as a PDG module over the symmetric functions. It has it's isomorphic just to the free PDG free PDG module sim n tensor this P complex, which is spanned by this basis element, this collection of basis elements. And this collection of basis elements is D-stable, and you can compute its cohomology or analyze its PDG structure. You see that this is just a tensor product of each individual each individual variable, okay, corresponding to each individual variable. So the first variable becomes, so because of the twisting we have introduced earlier, the first variable form a P complex, and likewise the second variables, etc. And this module over this module we have been considering is just this tensor product. And you see that as long as n is greater or equal to p, so the dimension of these modules goes from 1, 2, all the way up to n minus 1, to n, sorry. Okay, oh, oops. My computer is giving me a lot of trouble today. My apologies. Let me hide the lines. So what's going on? Sorry. Let me restart it.
This should happen at least once. I mean, to everyone, I think it's a rule.
Unfortunately, yeah. This always happens while I'm teaching on Zoom. Okay, so now we come back to this module. So the first one is a dimension 1 P complex. The second component is dimension 2 all the way up to n. So whenever n is greater or equal to p, you see that there is an acyclic or a free p complex of dimension p appearing. So last time, as we have said, whenever you have a free module over H, and the tensor product of H with arbitrary H module is always free, right, or always projective. So this guy will always be a cyclic in the homological sense. So this module is always a cyclic whenever n is greater or equal to p, and in particular, its endomorphism algebra is always an acyclic p differential graded algebra. So this endomorphism algebra controls what happens in this PDG category. Therefore, this follows from a slightly more general result that saying that whenever you have a quasi-isomorphism of P differential graded algebras, induction and restriction along this quasi-isomorphism give you mutually inverse equivalences of triangulated categories. So in particular, if your PDG algebra is a cyclic PDG algebra, so the inclusion of 0 is a quasi-isomorphism, then the derived category completely collapses. So induction restriction to the 0 category is a mutually inverse equivalences of triangulated categories. So this theorem is not very hard to prove, but it essentially uses what is in Bernstein and Lenz's book of how you prove the same theorem for differential graded algebras, and it adapts itself in the PDG setting as well, or homological algebra setting. All right. Okay. So finally, before we move on to today's main topic, I want to emphasize that there's a somewhat small surprise, at least to me and Ben when we did this work, is the uniqueness of this P differential structure. So Aaron Lauda's factorization of the idempotence in general is not quite unique. So in some sense, this is saying that if you have an algebra and you have a family of orthogonal idempotents in the algebra, you can conjugate this family of orthogonal idempotents by any automorphism of the algebra, and they remain idempotents in factorization of idempotents. So so naturally you would expect that there are many EF and FE decompositions in the story that are compatible with the P differential, but this is actually not the case. So in the presence of a diagrammatically local differential, not even necessarily the differential we define here, but any compatible differential with local relations, we have seen that up to conjugation by diagrammatic automorphisms, the differentials we define here are the unique ones that are compatible with the EF filtration, EF fantastic filtration. Okay, and secondly, Lauda's factorization of idempotents are also unique, the unique choices that's compatible with the differential. So in this sense, this story becomes much more rigid than they normally are in the abelian sense, in the usual generic categorification. So for this reason, we call this kind of filtrations really fantastic. It's not only there give you a beautiful structure, but it's also quite unique in some sense. All right. So that's all I plan for explaining categorification of quantum SO2. But now we'll move on towards its basic two-categorical representation theory. All right. So our goal is towards a tensor product representation construction at a prime root of unity. All right. So as a motivation, again, we'll go back to the original dream of Crane and Frankel, that is to lift combinatorially defined 3D Witten-Rastinkin-Turayev TQFT to a 4D TQFT. But this important ingredient in this 3D topological quantum field theory is the fusion ring of certain tilting modules. So essentially, this is you restrict your weights of SO2 representations to certain region called the fundamental alcove, and throw away all the representations that are away in a systematic way. So you throw away all the negligible modules, morphisms in the representation category, and the resulting thing, tensor representation category of quantum groups at roots of unity is called the fusion category of tilting modules. But so as a first step, what we would like to do is, of course, to categorify tensor products of SO2 representations at the prime roots of unity, okay? At the prime pth root of unity. So to do this, let's start with what wild modules look like at generic Q, and we'll give two constructions of natural geometric and categorical construction, combinatorial constructions of wild modules. So both admitting fast generalizations. So for SO2, the wild modules have a natural geometric and algebraic construction as below. But to do before this, let's recall what the wild module of highest weight L looks like. So it's an L-dimensional vector space. So I'll use a green dot, to label its basis.
L+1 dimensional.
Oh, L+1. Sorry, thank you. It's L+1 dimensional vector space over CQQ inverse, if you want, or C rational function Q, or at the root of unity, it's just over a cyclotomic ring. So this has the same structure with basis, but E and F either raises or lowers the weights by the corresponding by 2. And the idempotent algebra acts on this UQSO2 dot, act on this by the lambda region projects onto the corresponding lambda weight space, or otherwise act as 0 if the weights don't agree. And E and F just raises and lowers these degrees. So what is the geometric description of this representation? So a very natural and probably this goes way back to a work of probably Bernstein and on category O, that they observed that if you consider the category of sheaves, or G of L constructible sheaves on the Grassmannian K-planes in L space. Okay, so well, I'm overcomplicating the situation a little bit. So there is only a single orbit in the in this geometry. So you're essentially considering constant sheaves on the entire variety. So then the Grassmannian of K-1 and K planes, the two-step Grassmannian serve as the so-called incidence variety between these two varieties, right? So the Grassmannian of K-1 plane sitting in K plane sitting in the C of L has two natural forgetful functors. Pi1 goes to forgetting the K-1 dimensional plane, and Pi2 forgets the K-dimensional plane. So using these two functors, forgetful maps, you can define two functors on the corresponding sheaf categories. So these are corresponding pull back and push forward and push forward and pull back sheaf functors. So up to some gradient shift, you can see that E and F, the data of this VK together with this SO2 functors categorify this representation VL of the wild module we have described. Okay, so this is in some sense the weak categorification before you specify what the two morphisms are. So algebraically, if you want to give a combinatorial model, there's relatively easy model to think about. So you can describe sheaves over G constructible sheaves over this Grassmannian as DG modules over the cohomology ring over the constant sheaf. So that's the X algebra of the constant sheaf is the cohomology ring of the Grassmannians, so of K-planes in L space. So let's denote this ring by HK. And because this ring is always evenly graded, it's always a formal DG algebra. So you can write equivalent, describe any sheaf here as modules over the DG modules over the HK, and forget about the differential because it's formal. So this gives us an algebraic way to describe this categorification by replacing all the geometric categories by the corresponding modules over the cohomology rings. So here you replace Grassmannian of K-planes by HK and K-1 by HK-1, and the two-step Grassmannian by a module over this HK and HK-1. So the cohomology ring of this two-step black variety. So both the geometric and algebraic constructions admit vast generalizations. The geometric ones in ADE types generalized by Nakajima quiver varieties, and in all finite types by cyclotomic KOR algebras. So in non-simply list types, I don't think there's known geometric meaning of cyclotomic KOR algebras. You can think of them as some, as my code would always tell us, some quantum sheaves and quantum spaces. So so let's try to describe this later, the latter description in this context of KOR, cyclotomic KOR algebras or Neal-Heck algebras. Right? So because V of L is a highest weight categorification, you can think of it as behaving very much like a highest weight representation. So everything in this categorification can be obtained by applying lowering operators to the highest weight vector, or in this case, highest weight category. So V0 in this case is a highest weight category, must have the simplest structure. So in this case, it's just graded modules over a vector space. So it's not very hard to describe. So V0, actually, if you think about the previous story, it's just sheaves on the point. So it's equivalent to a K-graded vector spaces. And all the other categories you have seen earlier can be obtained by iterated lowering operators F to the K to this very simple category, vector spaces. But on this category, now we have two morphisms in modern categorification. So there are things acting on this functors. Okay, so we have introduced this multiplication by F to by a dot and the crossings on this F to the kth power. And if you think about it, what's F to the kth power? That's starting from a point. That's just a K-step partial flag variety in L space. Okay, and so on each of this partial flag variety, there is multiplication by Chern class of the associated line bundle. So that's the ith Chern class, Ci, C1 of the ith Li. And this crossing is given by the divided difference operator on the corresponding Chern classes. So that's how this operators act on the cohomology of the unstepped flag variety. And they are bound to satisfy these Neal-Heck relations together with the so-called cyclotomic relation, because the first, where you see L dots on the first strand annihilates the entire picture. This is because the choice of the first line is actually a choice of a line in P1, in F, in C of L, and that's just PL -1 choices. So the first cohomology class X1 to the Lth power has to be 0 on the first line. So using this, you can give a very nice algebraic description or combinatorial description that the cyclotomic quotient of this Neal-Heck algebra is subject to this equation. That whenever you see X1, the polynomial generator to the Lth power on the first strand annihilates the entire picture. So this quotient algebra is called the cyclotomic Neal-Heck algebra, categorifies the UQSO2 module VL. And moreover, Neal-Heck, each of this Neal-Heck algebras appearing in this direct sum decomposition is Morita equivalent to the center of this algebra, which is isomorphic to the cohomology ring of the Grassmannian of K-planes in L space we have seen. So you see that we're not, that's why this is equivalent to the classical description of categorical SO2 representation. Okay, so again, both stories generalize vast to arbitrary finite ADE types, and so using categorification, you can actually turn some relatively hard to understand categories, for instance, like sheaves on Nakajima quiver varieties, to relatively simple combinatorial gadgets like cyclotomic quotient rings and its modules. So now, using this beautiful picture, we want to see how this story extends to categorical actions. But before, I think we should take a brief break. It's almost 25. All right.
That's a good time for it. We'll reconvene at 10:30. In the meantime, if there's questions, please ask them. We should have added to the exercise sheet that stuff about the symmetric the polynomial ring over the symmetric polynomial. So that would have been a good one.
Yeah. Yeah, at least in the rank 2 case, that's a very good exercise to do.
I have a question. It was a bit fast for me when you were talking about equivariant sheaves on these various Grassmannians. Could you just say like what all these types are and in what sense this is like a categorical action of SL2?
So this is saying that, well, I'm not being super precise here. You have to take some mixed sheaves here on these varieties. And secondly,
are they constructible or
constructible sheaves along the strata of GOL orbits? So locally constant sheaves on the entire variety, essentially. And secondly, so why they're categorical SO2 action is that when you compute the commutator of E and F and E, their difference is essentially with the mixed structure, they're multiples of the identity functor, so with gradient shifts. So that's why it's in weak categorical SO2 action where you don't specify the morphism. So the SO2 acts categorically on those categories.
Thanks. What's the reference for this material?
Ooh, I think a good reference is actually Aaron's paper on SO2 categorification, but he used this, describe everything in terms of cohomology of the flag varieties. And also you can look at Countess, Kennedy, and Licata construction using cotangent bundles of these varieties. So cotangent bundles of Grassmannians are actually the corresponding Nakajima quiver varieties, but the constructible sheaves are equivalent to D modules over there. So it's an equivalent description as well, I guess.
Great, thanks a lot.
No problem.
Gio, I have a question about notation.
Sure.
If you would go back maybe one page or 2 pages.
Yep.
You have V subscript and V of K, like Is V sub L is the categorified vial module. What is
Yeah.
V of K?
It's the corresponding K weight space
Of
in this.
V sub L, or
Yeah.
okay,
Of V sub L. Yeah.
thank you.
No problem. Yeah.
Let's begin.
All right. Thank you for the questions. And so now let's come to how we can try to extend this beautiful pictures by previous constructions, either geometric or algebraic. So let's simplify the situation a little bit. So suppose we're given a family of symmetric Frobenius algebras. So we have seen a lot of Frobenius algebra appear in this story, but now let's think of these AKs as a cohomology ring of flat varieties or of Grassmannians. So these are analogs of families of symmetric Frobenius algebras coming from cohomology rings of some space. And MK is a family of right AK modules. So just very general modules. Sometimes you see this in the Morita equivalent context, but the important thing is that now we require MK. MK can be more general, not necessarily just projective modules over AK. And we consider the commuting ring BK, which is the endomorphism ring of the module MK over this AK, so it acts on the left. So it's in this way, MK becomes a BK-AK bimodule, okay? So, and they fit into this natural adjoint pairs. So you can tensor induce along MK from AK modules to BK modules. And it has a natural right adjoint called the Zergel. I explain where this S of K comes from. So it comes from Hom of MK. This S functor is given by Hom of MK out of over BK into an arbitrary module. So they are natural adjoint tensor Hom adjunction. As we have already seen in the Hopf algebra context, this very general tensor Hom adjunction. And assume furthermore, we have functors acting on this AI module category, as we have seen in the cohomology ring of Grassmannians. So this EIJ are played by the roles of cohomology two-part, two-step flag varieties regarded as a bimodule over HK and HK minus one or HK plus one. And tensoring product with that module gives you a functor going from one module category to the other. So this entire story now fits into a diagram. So this is, you have a natural SL2 action or a natural categorical action by collection of functors is given by a collection of functors acting on this collection of module categories such that EIJ composed with EJK is isomorphic to EIK as functors. So we have this diagram. And given this right modules over each AI, now you have extended a little bit this diagram by this connecting functors JI and SI, okay? So now we can, using this picture, now we can define these functors, for instance, between BI module categories like this. So you hypothetically declare this diagram to be commutative by declaring this EJI prime between BI and BJ by going this way. Okay, so naturally follow its direction. And of course, you want this equation to hold on the BI module category as well. So you want, once you define EIJ prime to be JI composed with EIJ composed with SJ, and for this composition to be canonically isomorphic to the other way, so if this composition should be the same as composed with JK with JI should be the same as the other way, it's natural to see that all you need to impose is precisely that SI composed with JI is the identity functor on each AI module category. So if so this double arrow going through AI just cancel out. So let's analyze what this does. So if you apply this functor SI JI to the module AI, the free AI module, so what you should get the right-hand side is just AI itself. And the left-hand side, SI of JI applied to AI is SI applied to M by definition of JI is this induction along MI. So it's the same as SI applied to MI, and SI is harm out of MI into MI now. So this precisely endomorphism of BI. So you are forced to have this so-called double centralizer property. By definition, BI is endomorphism of MI over AI, and now you also need to require AI is endomorphism of BI. So this is a very classical situation of the double centralizer property. And what's amazing about this special situation we're considering over symmetric Frobenius algebra is this very beautiful theorem of Curtis and Reiner, which we discovered has that already existed many years ago from the 1960s. Although I don't know what their motivation were in studying this context. It's about modular representation theory, but they didn't have categorical actions in mind, and it's just amazing that they already have this result. So, and strangely, it's not so well known. So I'd like to advertise this beautiful theorem that is definitely more general in the study. So let A be a Frobenius algebra and M a faithful A module, then this context of double centralizer property is satisfied. So then A and B satisfy the double centralizer property on M. So all you need is that A doesn't lose any information on the module M, so M is faithful. And furthermore, in this context, M is always projective injective. So it's both the projective and the injective module over B. So what you started with is just a faithful representation over A. So the role of M played over A and B are slightly different. So M doesn't, if M is a faithful module, it doesn't have to be projective. But when you turn to B, it's always projective and the injective. And so the harm out of the M functor, the S functor is always exact. And you can show that it's also fully faithful on projective B modules. So this is very reminiscent of the Zergo module, Zergo functor in category O. So we call this the generalized Zergo functor, but it actually existed even before Zergo's study on category O. Oh, sorry. Forgot to delete that page. So now let's try to give a sketch of proof of this beautiful result. Because it's a short course, so we should have at least one proof for every lecture. So without loss of generality, we assume that A is basic. So in its Morita equivalence class, you can always do this, and it doesn't affect its representation theory. And if you want to look at the non-basic case, you can go to our paper and see what to deal with. So when A is basic, the first fact is that whenever M is faithful, a faithful module, then M is always a direct sum of a copy of A with a complementary submodule N. Okay, so it's so always A occurs as a summand inside M. And to show this, so if you decompose A into a direct sum of indecomposable projectives, so because A is Frobenius, these are also injective modules, and pick the socle of each PI. So in this way, PI becomes the injective cover of its sockles because A's PI are also injective, and socle is a direct sum of all simple submodules in A. So that's in PI. So in this case, pick any non-zero element, and if PI is indecomposable, this socle is a simple module, so that the socle is generated by A times Xi. So since M is faithful, you can find that this Xi acts non-zerally on some element, and therefore this socle actually embeds into M. But by injectivity, the socle embeds in M, then the PI embeds inside M. And now you can do this for arbitrary PI, so therefore the entire module A embeds inside M. And again, because A is injective, it's actually a summand, as we have talked about last time. Whenever you see the nice thing about injective submodules in any big module is that it's always a split summand inside the big module. So Now, using this decomposition, M is isomorphic to A direct sum N. You can try to formally write this B algebra as a matrix algebra of these parts. So the first part is endomorphism of A, and the diagonal parts are endomorphism algebras of the corresponding modules. And the off-diagonal parts are the maps between A and N back to A. So this is formally you can write this decomposition. Now, if you have a element in the double commutant of endomorphism algebra of B of M, then X naturally commute with the corresponding idempotents in the two endomorphism algebras there, EA and EB. So these are identity maps on A and N. So using this, you see that X just act component-wise on A direct sum N. So it respects this decomposition because it commutes with the projections onto A and N. So in particular, because the endomorphism algebra of the first component A over this endomorphism ring, endomorphism A of B is just A itself again, there's always an element A0 such that X times A is equal to A0 times A on the left. Okay, so this B acts on the right on this first component. So you can find an A0 element acting on the left that has the same action as X. So what we're reduced to showing is that X also has the same action by multiplication by A0 on N. But now this is relatively easy. So now you can move any element N by using a matrix, upper triangular matrix N here from the element that's originally in A. So 0N comes from the 0, 1 element. This is in A direct sum N times some element B, where this element B is in off-diagonal matrix 0N 0, 0. So, but this element, this action commutes with the action of X. So therefore, 0 times Xn is, you can take it out. So that's the same as X acting on 0N because it acts component-wise, is the same as X times 0, 1 times this off-diagonal matrix. But we already know that X act on the first component by multiplication by A0. So that's A0 times this element. Okay? So in particular, the action of X on both components are just left multiplication by A0. So now to show that M is actually projective injective, it's not too hard now. So because by description, M is isomorphic to Hom of A into M itself, and A appears as a summand in M. So it's a direct sum in Hom of A of M into M. By definition, this is B. Therefore, M is projective. And now to see that it's injective, we use a little bit of the tensor Hom adjunction trick. So because A is a symmetric Frobenius algebra, A is isomorphic to A its dual. So M is isomorphic to M tensor A dual. And so, and taking double dual over vector spaces doesn't do any harm. So let's take double dual of the vector space. And now we use tensor Hom adjunction again. So this is Hom isomorphic to Hom of K of M into tensor A star into K dual. So we take, reinterpret this part with a single dual as this vector space and use tensor Hom adjunction to get this isomorphic to Hom A of M into A. But this is Hom of A into an injective module A is, if you know what this is essentially the Verdier dual or Serre-Functor on the A module category. So, but this guy is also a this guy is also a projective B module, essentially because the right A appears again as a summand of M. So this is appears as a summand of B again as a right B module. And now you're taking the vector space dual of a projective module and you get an injective module. Therefore the vector space dual is also injective and the result just follows. Okay, so this is some relatively not too hard algebra, but it's fairly general in context. So as a corollary, you always obtain that the centers of this AB are equal. So that's why if you have seen this context in categorical representation theory, why the center of Schur algebras or quiver Schur algebras is always isomorphic to cohomology rings of Nakajima quivarities, and that's the context why this. So I'll leave this as a very easy exercise. And so using this theorem, now you can easily deduce that in the categorical setting above, so if all I are symmetric Frobenius and Mi are faithful, then the categorical representation on the A module side extends to a categorical B module side on the BI modules. Okay. So, to be more precise, actually, we have to restrict ourselves a little bit on projectives. So this functor of tensor Hom is not the ideal situation, actually. So because the functors EIJ primes we defined earlier would rarely send projective modules to projective modules. So instead, we simplify this situation by considering the dual module, Mi check, because Mi is actually a projective B module. So taking its BI dual doesn't really lose information on B, on Mi. So, but it has the effect of turning it into an AI BI module, switching the rows of AI and BI. And now it has the right adjoint of the SI. So this is, that's the only context, only difference. So a simple lemma, relatively easy exercise to show that is Mi check, when you take the Hom of Mi into Bi, whenever you have this double commutant situation, is isomorphic to Hom of Mi into Ai. And actually, in this case, it's also isomorphic to Mi vector space dual. Okay, so I'll leave this as an exercise again. And then this, this module Mi check also satisfies the double centralizer property. And in this context, you can consider the right adjoint of Si instead of the Ji's earlier, and this categorical setting also extends to the previous, just as the same as the previous context. But the only difference is now that if EIJs actually preserve the additive envelopes of this direct sum of Mi stars, this dual modules on this AI side, then these functors EIJ double prime behave better homologically. So it sends projective BI modules to projective BI modules. So on the K group side, there's no difference. It's easier to study its actions. So you don't need to take resolutions in terms of modules. So it directly preserves projective modules. So the context is very similar. So now we just want to adapt this very general framework to quiver Schur algebras. To the particular situation we want to study. So now let's specialize AK to be the cohomology ring of Grassmannians or its Morita equivalent analog, the cyclotomic Neal-Heck algebras. So we want to find a collection of modules that are preserved under functors E and F. So the modules are already provided by variations of work of Hu and Mathis and independently by Ben Webster. So, but Webster considered actually more modules than needed. So to introduce these modules, let's fix some combinatorial data. So fix L in N. A Neal-Heck partition lambda is of weight K is a decomposition of K into L parts by ones or zeros, or we also call them boxes or empty slots, such that the number of ones is equal to K. So the collection of all such partitions is denoted by the script L and K. So in this case, for instance, when K equals 1 and L is fixed, you can just put a 1 in some spot, choose a spot among the L numbers and put 1 there. So translated into Young diagrams, it's empty boxes everywhere except in one, empty slots everywhere except in one position, the ith position. So whenever you're given such a neo-Heck partition, Hu-and methods considered in a right ideal in the cyclotomic neo-Heck algebra generated by this monomial. So y1 to the L minus j1. So where ji's are the positions you have a single ones. You have a ones or boxes. So you define this monomial and consider the direct sum of all such modules, the direct sum of all lambdas PLK, and so as a right module. So and the Quiver-Schur algebra in this case is just the endomorphism algebra of this right ideals. So to consider this continue discussing these examples, when k equals 1, this ideals just corresponds to the monomial ideal generated by y to the L minus first to the ith power, and whenever lambda has a single box in the ith position. So then this Quiver-Schur algebra FSL with a single of k equals 1, weight 1, is isomorphic to the Quiver algebra of L vertices with the relations 1 to 1 equals 0 and all loops at vertices are equal. Okay, so that's a Quiver. That's a particular case of Quiver-Schur algebra. And I think next week in Josh's talk, he will talk about more some important variations of this story. So a key lemma of Hu and Mathis is that this collection of modules is always faithful and self-dual, so satisfying both conditions we required earlier in the AB context of the corresponding modules. And consequently, these functors E and F preserve the additive envelope of this collection of right modules, and in the corresponding induced functors categorify the quantum SO2 representation C2 tensor L. So geometrically, if you want to think about what's happening here, is this SK of L describes the Borel constructible sheaves of the corresponding Grassmannian varieties. So the geometric functors are still realized by the same two-step partial flag varieties, but you just change the constructibility with respect from G to B, from GL to the Borel part. So in the last few minutes, I'll just quickly go through what happens at prime roots of unity, and actually the generic story is already similar enough to what happens at roots of unity. So earlier we have seen that the neo-Heck algebra has a p differential given by this way in the previous lecture, and it actually descends to the neo-Heck KL since differential preserves the cyclotomic relation. So this PDG category, in some sense, categorifies the while module, but the categorifies has to be putting quotes because if you directly take the derived category of this PDG algebras, it's actually smaller than the while module. So as you will see in one of the exercises, because in the PDG world, Morita equivalence is a very subtle relation. So in the PDG land, the previous theorems in our joint work with Kovanov and Sazin actually generalize, it's not very difficult. So if this functors, collection of functors preserve the filtered PDG envelope, so this is a notion that I haven't really introduced, but it's the analog of the additive envelope in the filtered in the PDG world. So you require a module to be the filtered envelope if it has a filtration whose subquotients are direct summands of these modules. Then this functor extends to a categorical action on the B module, PDG module over B side, and descends the analog of projective modules called cofiber modules in the PDG world to cofiber modules. So it actually descends to the K group relatively easily. And in the particular case of Quiver-Schur algebras, you see that these functors E and F does satisfy this condition, and that's in my paper with Josh Sazin, that they preserve the filtered PDG envelope, and therefore there is a categorical EF action on the Quiver-Schur algebra side. And when you pass to derived categories, this action categorifies the quantum SO2 action on V1 tensor L. Okay, I think I'm out of time, so but at least let me give you the example of curvature algebra in the last minute. So the curvature algebra inherits the P differential, as we have seen in this particular case. As endomorphism algebra, the rightward going arrows just has a loop attached to the end, and the leftward going arrow is 0. And in this case, you can study it's the PDG derived Grothendieck group is isomorphic to the L minus second weight, highest weight space of V1 tensor L. So this is an L dimensional space on the right hand side. Okay, and further in my work with Josh, actually we have exhibited a categorical braid group action on the entire derived category of this particular weight space. And we do expect this braid group action to extend to the entire curvature algebra, but it's not quite done yet. Okay, I think I should probably stop here. There are some slides left, but this is a good point to stop.